Hello friends, welcome back once again. This is Nagaraj SK, Lecturer of Computer Science and Engineering Department, Jain Polytechnic, Belagavi. So in this session, we'll move to the next lecture number 36 and 37 of Unit 4 Divide and Conquer. So here I'm going to brief you about quicksort, what quicksort is, how quicksort works, and what are the examples of quicksort. So the quicksort is the other important sorting algorithm that is based on the divide and conquer approach. Unlike merge sort, which divides its input elements according to their position in the array, and quicksort divides them according to their value. We already encountered this idea of an array partition in the previous section where we discussed the selection problem. So a partition is an arrangement of the array's elements so that all the elements to the left of some element a of s are less than or equal to a of s, and all the elements to the right of a of s are greater than or equal to it, such as that is two subarrays a of one low to mid and mid plus 1 to uh, n, that is such that a of I less than or equal to a of j for all L less than or equal to I less than or equal to M, and M plus 1 M plus L M plus 1 less than or equal to J less than or equal to N, and no need for merging in quicksort. Like merge sort, there is no merging here, and each of two subarrays can be sorted independently. So obviously after a partition is achieved, a of s, that is a of s will be in its final position in the sorted array, and we can continue sorting the two subarrays to the left and to the right of a of s independently. For example, by the same method. Note, we have to note that particularly the difference with merge sort, there the division of the problem into two subproblems is immediately, and the entire work happens in combining their solutions. Here the entire work happens in the division stage with no work required to combine the solutions to the subproblems. Then we have the partition, how to partition that, right? So will be taking place here partition thing in the uh, quicksort algorithm. So as a partition algorithm, we can certainly use the Lomito partition, that is which is discussed in further things. So alternatively, we can partition a of 0 to n minus 1, and more generally its sub array a of l to r, that is low to right. 0 less than or equal to L less than R less than or equal to n minus 1, while the more sophisticated method suggested by CAR Hoare, the prominent British computer scientist who invented quicksort. CAR Hoare, he is the prominent British computer scientist who invented the quicksort algorithm. So here let us discuss about the partition function, how this function works. So the name of the function is partition, return type is int, and it is taking three parameters: an array, low, that is L and R of type integer. So within a an array A, that is the elements are rearranged in such a manner that if initially t is equal to a of L, then after completion a of q is equal to t for some q between 1 and r minus 1. So a of k less than equal to t less than or equal to t for L less than or equal to k less than q, and a of k greater than equal to t for q less than or equal to k less than k then less than r. q is returned. And we are considering here some of the variables like of type p is equal to a of m and int I equal to m, then j equal to p. Then do what we are doing, do I plus plus while a of I less than v, then do j minus minus while a of j greater than v. If I less than j, interchange, and we are calling interchange function a of I comma j while I less than j. A of m equal to a of I, then a of j equal to v, return j. Inline void interchange, type a int I int j, type p equal to a of I, a of I is equal to a of j, and a of j equal to p. This is how the partitioning takes place. That is, s is nothing but is a split position. That a of s I explained you people, that is a split position. Here here it is v, that is the splitting position. Then we have an example for quick sort. It is 65 70 75 80 85 60 55 50 45 plus infinity at the end of the list, and I is 2, j is 9 initially. So first element we are leaving because that we are selecting as a initial element, and no need to consider that, because with that we are comparing with all the other elements. So 65 will be compared with all remaining elements from 2 to 9. So 65 is less than 70, no need to swap. 65 is less than 75, 80, 85, 60, right? Then 55, 50, then 45. So 45 is the least, so that will get swapped. That is 65 and 45 will get swapped, right? So 65 will be as it is because we are not selecting that, right? So 70 and that is index number 2 and index number 9 will get swapped. So 45 will come to the second index, 70 will go to the last index, that is sorry, ninth index. Last index is 10th index, that we are adding plus infinity, that indicates end of the list. Then 65 45 in the first sorted array list. Then 75 will be compared with all other elements 80 85 60 55 50 and 70. So 3 and 8, 75 and 50 will get swapped. So 65 40 50 is the sorted array, 80 85 60 55 75 70 plus infinity is the remaining unsorted elements. So similarly all other elements will be compared and swapped with each other. And I told why we are using their infinity, right? So just to indicate that end of the list. Then we have quicksort function, void quicksort int p int q. It is a method. Quicksort is a function. It is taking two parameters p and q, sorts the elements a of p then a of q, which resides in the global array, that is a of l to n, sorry 1 to n, into ascending order. A of n plus 1 is considered to be defined and must be greater than or equal to all the elements in a, that is from 1 to n. If p is less than q, then do some things. Why? If there are more than one element, divide p into two subproblems. If more than one element, divide p into two subproblems. Int j equal to partition a comma p comma q plus 1. J is the position of the partitioning element. Then solve the subproblems by calling the quicksort method itself, quicksort function itself, by passing respective parameters, respective values p and j minus 1. And for the first half, then the second half j plus 1 to q. There is no need to merge them, that is there is no need for combining the solutions. This is how the quicksort function works. Then we have to analyze this quicksort algorithm, that is how much time it takes for splitting, merging, and what is the best case analysis of this quicksort, what is the worst case, what is the average case. So best case, all splits happens in the middle theta of n log n. So we'll be getting the best case analysis which is belonging to theta of n log n. So you please go through these steps, that is solving how to solve this best case analysis of quicksort. So tb of n equal to 2t best n by 2 plus n for n greater than 1. So tb of 1 equal to 0. So just go through these all steps and you will come to know that what is best case analysis of quicksort. Then similarly we have worst case analysis which is belonging to theta of n square. Then we have average case analysis of quicksort, that is random array theta of n log n. ca of n is much less than cw of, that is average case of n of quicksort is much less than worst case complexity of n of quicksort, under the assumption that partitioning element p has an equal probability of being the ith smallest element. The recurrence is given by ca of n is equal to n plus 1 plus 1 by n for some 1 less than or equal to k less than or equal to n. Then average case complexity of k minus 1 plus ca of n minus k for all n greater than 1, ca of 0 equal to 0 and ca of 1 equal to 0. Solving above gives us the average case analysis of n belonging to n log n. Then let us summarize what we discussed so far. We discussed so far what is quicksort and how quicksort algorithm works, and worst case, best case, and average case efficiencies of this quicksort algorithm, and finally examples of the quicksort. So if you are having any doubts in this, please do ask your queries, and thanks for watching. Thanks a lot.